Well, when I last left you, we were lamenting the fact, or I was lamenting the fact, that we can't really get the fitted values, much less the residuals, from JASP's available options. Now, if you do find a way, please let me know. I'd be glad to hear it. So this is the original data set. It's much easier to manipulate the data set in Excel. So we're just going to go through the process that the book looked at and essentially set up that prediction model where the predicted value for any given data point is the grand mean plus the whatever effect it gets from being in a particular river plus the effect it gets from being in a particular site. That's going to be the predicted, and once we get the predicted, the residuals are quite easy. And when I say predicted, I mean the same thing as fitted when the book says fitted. So first thing we need to do is get the grand mean. I'm going to use variable names that don't have spaces just because some software like SPSS, I forget if JASP does or not, but it will not accept variable names with spaces in them. Now this grand mean is really just the average of column C, and it doesn't matter which data point you are, your grand mean is the same. Once we get to the river effect, what this is essentially saying is the rivers, these four rivers, each have different average levels of iron. So how far is this average off of the grand mean? In symbols, we're going to say the average of these three. This is coming from the Grasse River. Grasse, probably something like that, is 598. And then we would want to subtract that, or subtract the grand mean from that. So just by being in the Grasse River, on average, you're going to be about 193 whatevers of iron higher than the average of the 12 data points. So it gives you this kind of positive effect, or this likelihood you're going to have a higher iron concentration in this river than on average for these 12 data points. Now we want to copy this down. Notice the way that I designed the formula C2 through C4. If I were to paste this formula down one cell, it would then take the average of these three, which would be 2 from the Grasse and 1 from the Oswegatchie River, which isn't at all what we want. The grand mean would update since it's the same for everyone, but we couldn't just cut and paste this formula down. However, notice that if I copy this, I just did a Control-C and paste it here, here, and here. Let me just click into maybe say this one. So notice what this is doing. It's taking the average of these three, which are all the Roquette River, and subtracting out the grand mean. So these four formulas are valid. What we really need to do now is all three of these data points in this particular river have the same river effect. So we need to copy these down, copy these down, and copy these down. But if I just tried to copy this, it's not going to give me the same number because, again, as I said before, it's copying the formula. So I'd say a nice way to do this is just select the whole column, copy it, right-click, paste special, and values. Now this is the actual value, not the formula. So if I want to drag this down, I can copy that river effect right on down there. Okay, and then we're going on to the site effect. Where in the river was it collected? My assumption is there's going to be more iron upstream than there is downstream or midstream. And I'm going to take the average. So let's start with the upstreams. I'm going to grab all four upstreams right there. So that's my average of the four upstreams. How much of an effect do I have? Well, I have to take the difference between that and the grand mean, and that would be the site effect. And here I can copy down, because notice what happens here. When I naturally drag the formula down, it's going to grab all the midstreams because they're equally spaced out. If I had several upstreams and then one midstream, if there weren't equal numbers, this would not work out. But because it's such a clean data format, it works out nicely. However, now I can't just copy this down. These numbers here are meaningless, or would be meaningless if I use them. What I really need, this is the upstream effect, this is the midstream effect, this is the downstream. How much different on average are the upstream sites, the midstream, and the downstream from the grand mean? So I need to copy this over and over, and in order to do that, again, whoops, I'm going to copy it to the clipboard, right-click, and paste special, values only. I think I did that there. And now we can just cut and paste those down. Okay, this is great because now I can finally calculate the fitted values. So the fitted values now is just the sum of the grand mean, the river effect, and the site effect. So for example, based on what I know about the Grosseter River, the overall average of these 12 data points, and the fact that this was an upstream data point, I would predict that the iron level was about 860, and I'd be a little short. We could go ahead and create the residual column now too. So the residual is where I actually was minus where the model would have predicted me to be. So I was 84 above where the model would have predicted. Now this is nice. I can just copy this down, and same thing for our residuals. I could drag that formula down if I needed to. But here I now finally have a predicted value for each of the 12 data points, and then how far off from the actual was I with these 12 points. Just as a quick check, the fitted values here, if I select this column, notice that my average, you may not be able to see this, but at the bottom of the screen it should give you an average 404.833. That should be the grand mean. The grand mean of the fitted should be the grand mean of the actual, and this is true of this type of model. The residuals, on the other hand, if I select them, I should get an average of 0. Remember that one of the assumptions is that I'm centered on my fitted line, that these residuals, if you take the average, will end up right on the fitted line. And this method that we're using guarantees that. So we don't really even think much about that assumption because we're using a mathematical method that guarantees that our residuals will have an average of 0 if we did the calculations right. Here's where it would pop up if you had made a calculation error. And for that matter, the sum is also 0. That's why the average is 0, is when we add the sum, all these residuals up, you would get 0. Now what we really needed to do, this was our goal all along, is the fitted versus residual. We're going to go to insert a scatter plot. And here's what we were really going after. So let me center this and then we'll talk about it. Okay, so what we're looking for here, the book gives us a few things. Is the variance constant? To be honest, there really aren't enough data points here, and you notice the test of homogeneity back in JASP didn't even let us run it. At every level of the x, is there equal variance in the y? I mean, it's really too hard to say here. Are there clusters? Not so much. But the thing that really gets us here is there a departure from a straight line? Is there some indication that there's some kind of curvature going on? And in that sense, I would say that there looks some kind of quadratic, or I mean, there really aren't enough points here to tell anything definitively. But I would definitely have some thoughts that these aren't randomly scattered around some trend line, scattered above and below. It does look like there's a trend here where they're going down and then going up. So this one, we're pretty questionable here on the assumptions. Moving to part D, the thing that really is a knife in the model here is this point right there. So at first, doesn't seem too strange this side, then maybe it's further away, maybe it's like an outlier. But the issue here is, notice that our x-axis is the fitted, in other words, the predicted, where we predict these data points will be, and we're in the negatives here, so we're somewhere between negative 50, it looks like a little over a negative 100. This right here is saying that there would be negative levels of iron in the model, which certainly couldn't exist, or sorry, negative levels of iron in this particular sample, wherever that happens to. I mean, we could look here. It's this one right here. So Raquette downstream, that's predicted that this would be negative 137 units of iron. So that's an issue. That's a big issue with the model that we would need to somehow address in how the model is being created here. So what does all this mean? What does it mean? It means that, yeah, okay, we have statistically significant p-values here on the river and site. But we have to be a little careful with this model that we're trusting here. We've already seen some fairly severe limitations, especially that negative point was a clear indication that things aren't going well. Even with a few data points, it's predicting something way into the negatives. Now, it doesn't mean that the model is useless. It means that we probably can't do too much with these p-values, and I think the book actually discusses this towards the end of the chapter. But what we can see, we can still see patterns across these. I think if we looked at some descriptive plots, maybe each line was a different river, and then the site was a horizontal axis. Okay, so here we do see the rivers. We can see visually at least that the iron levels do tend to go up here as we move downstream, which I guess makes sense. The water would slowly collect it downstream. We can also see that the Raquette River does seem to have lower levels of iron than the other three. So there are things we can get out of the data. It's not useless. But using the ANOVA table here to give us a quantitative statistical significance, this isn't really perhaps the right use of this data.